Okay, so now we're going to talk about Hardy-Weinberg equilibrium. And so that's just this simple situation where there is a relationship, a direct relationship between allele frequency and genotype frequency. So in general, we talked about allele frequency and genotype frequency can be independent. We talked about a specific situation where allele frequency was the same, but in one case you had every single individual being heterozygous, and then the other situation you had a mixture of both homozygous genotypes. And so that's a situation of how there can be differences between genotype frequencies when allele frequency is the same. But in certain conditions, we can predict genotype frequencies with certainty using allele frequencies. And so there's three really important assumptions that go into this, and so you should memorize these assumptions for the test. So one is you need an infinitely large population. Two, you need to have random mating. So each individual of a population randomly chooses which individual to also mate with. And then finally, no evolutionary forces can be at play. So you ignore things like genetic drift, migration, selection, etc. And so, these are obviously never going to happen in the real world. But if you had these three assumptions occur, then basically for a fact what the three different genotype frequencies are given an allele frequency of P and Q. And so, this is basically the idea is that you would, in order to create a new individual, you would have a mating. So you'd have a sperm gamete and an egg gamete come together in order to form a new individual. And so if you asked, what is the probability that that individual is big A, it's just a Punnett square is kind of the idea. And so, again, when we talked about Punnett squares, we said, okay, what are the two different genotypes that the gamete could have? And then what is the probability of each? And so here we have a Punnett square where P is the probability of a big A and Q the probability of a little a. And so because you're randomly pulling individuals, the two sides of the square will be the same. And so the probability of there being an individual with this genotype is P squared. And then there's two different ways you can get the heterozygote. So each one of these is PQ, but if you add those two together, the probability is 2PQ, and then the probability of the other homozygous is Q squared. And so now we go on from a situation where you don't know the genotype frequency unless you measure the genotype in all the individuals to a situation where you can infer it just having this information of the allele frequency. And so, if you add up, the allele frequency probabilities, they equal 1. And so this is also the case right here. So this right here would be summing up the three genotype frequencies. And so that is actually equal to P plus Q squared. So you can use your math in order to show that this expression right here is the same as this, and so that would be the same as 1 squared. And so again, the genotype frequencies all have to add up to 1. So how do you use Hardy-Weinberg? So this can be very, very useful for inferring genotypes that you typically can't see. And so this is useful because it's very hard to distinguish carriers and homozygous. So in the cases of recessive and dominance, it's very hard to distinguish between heterozygotes and homozygotes. And so this allows us to use this frequency right here, the frequencies of individuals that actually have the disease or have the phenotype, and then you can use this information to determine the number of individuals that are carriers. So kind of an example of this is to calculate the number of individuals that carry this particular allele. So again, this was an allele that falls within a receptor of this protein CCR5, and so homozygous individuals are resistant to HIV infection. Heterozygotes are susceptible to infection but progress more slowly to AIDS. And so, if you had three individuals, you can simply use, because the particular change is a size difference, you can use a DNA gel after amplifying a particular region to determine kind of what the genotype is. And so this right here is a control lane. And so you can either have homozygous for this allele, homozygous for this allele, or if you have both. So what we're going to do here is we're going to actually calculate the genotype frequencies and the allele frequencies using the counting method. So this is not using the Hardy-Weinberg approach in order to calculate these numbers. And so here we've done 100 different individuals, and then we've ran these gels on all 100 of these individuals, and we determined the genotype. And so 79 of the humans that we tested have this genotype, 20 are heterozygote, and 1 is homozygous recessive. If we wanted to calculate the allele frequency, we would calculate the number of alleles. So this 79 individuals carry 2 copies, 20 individuals carry 1 copy, and 1 individual carries 0 copies. And so again, we can do that for the alternative allele. 20 individuals carry the delta 32 from the heterozygotes. 1 individual carries 2. And so the total number of alleles is 178 and 22, and those added together equals 200. So again, the total number of alleles in a population is 2 times the number of individuals. And so this right here would be P, and this right here would be Q. If we wanted to calculate the genotype frequencies, we would just use these numbers. So 79 divided by 100, so it's 0.79, 0.2, and 0.01. So what are the expected frequencies using Hardy-Weinberg equilibrium? So again, we start from these numbers. We start from the allele frequencies that was calculated for this population, and then we simply use the p squared, the T2PQ, and the q squared to actually determine how many individuals we expect to have each genotype. And so we can compare to the actual and so we can see these numbers are in pretty good agreement with each other. You can also do Hardy-Weinberg in conditions where there are multiple alleles. So an example of that is blood type. So if you recall from previous lectures, there are 3 different, why is this doing this? All right. There are 3 different alleles. So there's the A allele, there's the B allele, and then there's the little I allele. And so if you add those 3 numbers together, these would have to equal to 1. And so you'll see that they've added this third letter R in order to account for the fact that there's the third R. So now when we do the relationship between the allele frequencies, since there's this third allele, P plus Q plus R is what has to equal to 1. And you can do that on your own just to verify that these 3 numbers add up to 1. So again, for Hardy-Weinberg, you're just creating kind of a Punnett square and so the probability of being homozygote is just these probabilities. So again, it still remains p squared. If you wanted to know the probability, for example, it looks like they have a typo in this. So this one actually should be 2PQ. If you wanted to calculate the number of individuals that had this genotype, you would just do this part of the Punnett square right here. So basically this right here would be the IA IB square, and then same with this one right here. And so when you multiply these two together, you would do P times Q, and so there would be two of these squares, so again it would be 2PQ. If you wanted to calculate the number of individuals that were heterozygote, so they had the B blood type but they were heterozygote, that would be, you would just simply match up and identify the parts of the square that match that genotype, and then you would just add 2QR together in order to calculate that. This is 2PR, for example, for that. So pretty straightforward. The math initially seems a little bit complicated, but the way you get there is pretty straightforward just using this Punnett square. All right, so let's now move to a situation where Hardy-Weinberg can be more useful. So an example of this is if you wanted to know how many individuals were carriers for cystic fibrosis. So cystic fibrosis is an autosomal recessive disease, so it's very easy to calculate the frequency of this disease because the people with the disease have very obvious phenotypes. And so in Northern European ancestry, the number of people that have the disease is 0.0004. And so kind of what we're referring to are the percent of individuals that have that genotype, or sorry, I guess in this case, have that genotype. And so if you wanted to know how many individuals were carriers, that's much more difficult to determine unless you actually sequenced everyone's DNA within this population and you knew kind of like what is the causal allele for cystic fibrosis. But you can use Hardy-Weinberg to infer that carrier frequency. So if we assume this population is pretty close to Hardy-Weinberg equilibrium, then we can use this relationship to calculate these numbers. And so the way you do that is you assume that the number of people that have this genotype, this 0.004, that number must be equal to the Q squared from the Hardy-Weinberg. And so this allows us to determine the allele frequency of the causal allele within the population. And so that allows us to calculate Q is equal to 0.02. And so if we wanted to know the number that were carriers, we need to calculate 2 times P times Q. And so Q is equal to 0.02. We use this relationship P plus Q equals 1 to determine that the frequency of the normal allele is 0.98, and so we can simply multiply these numbers together, and then we can calculate the carrier frequency. So approximately 4% of individuals are carriers for cystic fibrosis. And so, if you consider how many people are in our class, there are probably multiple people within this class that are actually carriers for cystic fibrosis.